So last time I was talking about the principles of operation for this device, this integrated circuit tester that can also detect tri-state or disconnected outputs on the ZIF, which is kind of an unusual feature. And since then, here, after much soldering, is the finished product. And we've got a chip in the socket there. I'm not using the top two pins in this particular revision of the hardware because there was a problem in my understanding of what A6 and A7 did. These analog pins only operate as inputs. The other analog pins can also operate as outputs, but A6 and A7 unfortunately only operate as inputs, and I had used them on my ZIF socket. So I changed the software so that it ignores row 1 of the ZIF. The later revision of this software actually uses all pins, but the one I'm using on this Arduino at the moment has been modified with a hash define to skip those top two pins. Anyway, we can take a look at the software and see this thing in action.
So let's take a quick look back at the GitHub site. The GitHub site's got all the documentation for how to specify a test case. Highlighted there is an example of a test for an 8-pin chip, and the codes 1, G, H, Z and V are explained in the table below. It's a fictitious chip. But we can see that the table below is saying that if you want to specify that particular pin on the chip is VCC, well, use code V, ground is a G. If we want to specify that a pin is set to logic 1, we use 1, 0 for logic 0. C is a special case. That signifies that the pin is an input and it's a clock, and during the test it will be cycled. But we've also got outputs, and we want to make assertions about those outputs. So if we expect a logic low, then we'll specify that by saying it's an L. H signifies we're expecting a logic high. A Z, that it's a high impedance output. They'll be positively tested by the software using a pull-up, pull-down test. Sometimes, though, you don't care what the value of the pin is, and we can say that with an X. And other times, you're doing a bit of exploratory work, and you don't know what the value is going to be, or you're uncertain, so you can use a question mark in that pin position, and the system will test that pin and come back with a 1, a 0, or a Z accordingly. Slash can be used to signal that you want to repeat whatever the previous operation was, whichever that test was. When you run a test, you get some outputs, and beneath the test input, the system will print out the results on a pin-by-pin basis, and a dot in any position indicates that the expectation that you set was met. It's effectively a pass. But if you see anything else, it typically means that something went wrong. So an H indicates that you wanted something other than H, say a low or a high impedance, but you got a high, and a low signals that you got a low unexpectedly. Ones and noughts are a special case, and they're used when you've used the question mark on the input, and it's just telling you whatever it sensed. It sensed a 1 or a 0. So let's have a go at using that to specify the test for an empty ZIF socket. So here's our empty ZIF socket. Now, given that all the pins are unoccupied, we should expect all of them to be coming back with a high impedance state. So that's our test. It's a sequence of 22 Zs. So let's take that now and put it into the serial monitor and see what the hardware comes back with. So let's get the serial monitor up and running. Select the port. And what we get back initially is just the usage for the device. So we want to run a test against the device, and from the usage we can see that's T followed by a colon followed by the test pattern. So we said it was 22 Z, so let's do that. Okay, and it came back with a pass, and you'll notice that in the results there are just a sequence of full stops. That indicates that the expectation was met in each case. So pretty simple test. Let's take a look at what it would have looked like if, say, for instance, I'd made the assertion that the last pin there was going to be a logic high. So we get a fail. It's telling us that the last pin was the reason for the fail, and it wasn't a high that we got back, it was a high impedance state. So, right, let's try next something a little bit more complicated. Let's look at a 74245 transceiver. A little bit more going on there, and we can look at a couple of test cases for that too. Okay, so here's an extract from the datasheet for the 74245. And our first test is going to be what happens when we have the output enable pin set high. So that's with the outputs disabled. So what are the inputs going to be? So first of all, we need to identify where the power supply and the ground are. So they're signified with a V and a G, and that's pin 20 and pin 10 respectively. Next, we're going to set the output enable to 1, and given this is an active low, that effectively disables the outputs. And in this case, the direction pin, it's irrelevant, we don't care. So we're going to signal that with an X. Now, because the outputs are all disabled, we should expect them all to be in a high impedance state. So there's all our pins populated in the test case. The test case then is going to be this here. So let's take that and run that against the hardware with the 74245 in the socket. Okay, let's get the software going again. Right, so let's put that test into the serial monitor. T : followed by the test. Right, it came back with a pass. Now for our next test, we'll enable the outputs and we'll send some data from B to A. So let's go back and look at that. So here we are with the 74245 again. We've already got V and G marked. The output enable needs to be low this time because we want the outputs turned on. And that means that the direction pin does matter. And given that we want data to flow from B to A, that needs to be a low. Let's put some data onto the input pins, which are going to be B on this case. The lower 4 bits will set to 1, the upper 4 bits will set to 0. And we want some expectations then on what comes out on A. Because the lower 4 bits of B are 1, we expect the lower 4 bits of A to be logic high. And because the upper 4 bits of B are low, we expect the upper 4 bits of A to also be low. So there's our test pattern at the bottom. Let's get that and put it into the serial monitor and see what happens. And again, another pass. So just a quick recap then. Signaling inputs, we have the codes VG, 1 and 0. And for the outputs, we've got H and L and X for don't care. So I hope you found that useful and interesting. After I built the project, I had a hunt around for other devices which might have proven useful, and I thought I'd spend a few minutes just talking about the ones that I came up with. So these two devices stand out. They like the MCP 23017. They have 16 GPIO pins, but unlike the Arduino and the MCP 23017, these two devices have got pull-up and pull-down resistors. And what I think that would probably mean for me if I were to build this again is that I wouldn't need GPIO-H in my design. The single pin could play the role of an input and output. It could do the pull-up and pull-down as needed. Where these devices differ and where they're a little bit more inconvenient for me is that there's no DIP variant. There's a TSOP24 package and a tiny TQFN. So if I get a bit more competent with the soldering iron, then that might be an option. And if one was to actually build something like this and get it fabricated, then I guess you'd use those instead. So there you are. I hope that was useful. Thanks very much.